All right, so we got a fairly easy lecture today. Congratulations, you've made it over all the hard parts. So today we're going to talk about, finally, basic scheduling, which you've kind of already done. So this is just kind of formalizing it a little bit and making it into essentially questions that may appear on a quiz. So preemptible resources are kind of a generic term. So any resource can either be preemptible or non-preemptible. And a preemptible resource just means it can be taken away at any time and used for something else. So for example, you have your CPU, you can take it away, give it to another process, and then take it away from that process, give it to another one, and so on and so forth. So a resource that is preemptible, you can share through scheduling, so make sure everyone gets a turn, essentially. While a non-preemptible resource cannot be taken away without at least some sort of acknowledgement, otherwise some things might go bad. For example, disk space. I can't share a hard drive. I can allocate space for it, so I could say, hey, you can have, a 4 gig file, you can have a 4 gig file, but every single process, for example, cannot share an entire hard drive. You can't just swap it back and forth. And non-preemptible resources would be shared through something like allocations and deallocations. So, hey, I need space for a file, and then, hey, I'm done with the file, I can delete it, and then you can go ahead and use it for something else. And then note, for some like high performance computing and distributed systems, you may actually be able to allocate the CPU. So you can say, hey, I'm going to grab this CPU. You cannot preempt me. I will grab it for the entirety of my process. And you can't take it away because I actually need that control. I need it to run as fast as possible. So anyone want to name possibly another example of a non-preemptible resource? So if disk space is one, what's another one that we constantly allocate and deallocate? Huh? More generic. Memory, right? So memory is also a non-preemptible resource. I have to allocate it and deallocate it. And of course, with memory, it can represent the stack, the heap, all that fun stuff. So there's two things. There's a dispatcher and a scheduler. So a dispatcher is actually responsible for context switching. You may see it in other resources. And it's just whatever is doing the context switching, and that's called a dispatcher. So it's just another term you might see in your journeys through operating systems. While the dispatcher does the context switching, and then the scheduler is the high-level policy that decides what to context switch. So it decides what processes to run at any given time. And they have to work together. So the scheduler runs whenever a process changes state. So we're first going to consider the easiest case possible, where we have non-preemptible processes. So a process, once it starts, it will get executed until it finishes. So this is like the old batch systems where you just start a process, it runs till it's finished, and then after it's finished, you can run something else. So in this case, if you're the scheduler, you only have a decision to make when a process terminates and the CPU is free, and you just have to pick the next process to run. And then preemptive, which is kind of what we're all used to, just allows the scheduler to run at will. And if you are on a Linux machine and you do uname-v, so we can even run that. So if you do uname-v, that's actually one of the terms here. So this means it's a preemptive scheduler, and the kernel will tell you that. And then the other one here is SMP, that's symmetric multiprocessing. That just means you can support multiple parallel processors, and they're all the same. So the kernel will tell you what it supports. So if these options are here, it's like 99.9% of modern things. So now we know what they both mean. Okay, so when we discuss scheduling, we have to have some way to evaluate how good our scheduler is. And these are some metrics that you would want to keep track of. So first, you'd want to minimize waiting time and response time. So as soon as you start a process, you would want to get executed, or at least start execution on it as fast as possible. And that lag time from when it gets, when you say you want to run until it actually runs on the CPU at the first time instant is called the response time. So that's kind of your responsiveness, how fast your system feels. And then waiting time is just the total amount of time that process is waiting to run while between when it starts and when it finishes. Then if you're the scheduler, you want to maximize CPU utilization as well. If you have 8 cores or something like that, you want to be able to use all of them. You don't want idle CPUs because they're not doing any useful work. Then next, you might want to maximize throughput, so complete as many processes as possible if you only care about the absolute number of processes that finish. And then finally, the last metric, which is kind of at odds with all the other one, is fairness, where you try to give each process the same percentage of the CPU and try and be fair and don't pick any favorites. So our first scheduling policy, everyone's been using it for their entire life at their food trucks, everything like that. It's first come, first serve. You get in line, it's a FIFO queue. If you are the first in line, you are the first served, and it just goes in order. So that's the most basic form of scheduling, and we're used to that pretty much our entire life. So the first process that arrives gets the CPU, and they get the CPU in the order that they arrive. So it's just a FIFO queue in arrival order. So these are we'll use Gantt charts to illustrate the schedule for arguing about all these problems, and it's not as boring as Gantt charts for the software, or not software, but for engineering process courses. This is actually a pretty simple one where we just care about what's happening on a single CPU. So we're just assuming a single CPU. So in the table here, we have our processes, P1, P2, P3, P4, and then the arrival time, which is when the user wants to start all the processes. In this case, they're all going to arrive at time equals to 0. Then the burst time is just how long each process takes to execute, how many time units it takes, and we're just going to assume that we'll have an atomic time unit of 1 where we can't divide it up, just to make things easier. So burst time, also the total execution time it needs is here. So process 1 takes 7 time units, process 2 takes 4, process 3 takes 1, process 4 takes 4. So since they all arrive at the same time instant, we'll just assume that they arrive in the order P1, P2, P3, then P4. So if we do first come, first serve, at time 0, we have them in that order. You pick off the process that arrived first. So in this case, it would be P1. So we pick P1 to execute, and we're assuming non-preemptible processes, so it just runs until it finishes. So we start P1, it takes 7 time units, so it will, and then each bar there, it's a single CPU and 1 time unit per square. So it executes for 7 time units here, so at t equals 7, process 1 is done. We have another decision to make. We have to run either process 2, 3, or 4, and we just do it in the order they arrive. So we execute process 2, it takes 4 time units, then we execute process 3 after that finishes, which is only 1 time unit, and then process 4 after process 3 finishes, which is 4 time units. So one question you might ask is, what is the average waiting time? So the average waiting time, it's just a simple average. So process 1, how long did it wait? Well, it arrived at time 0 and it got executed immediately. So it waited for 0 time units. Process 2 arrived at 0, didn't start executing to time equals 7, so it waited around for 7 time units. Process 3 got executed at t0, didn't start executing till t equals 11, so it waited around for 11 time units, and then process 4 waited around for 12 time units. So if you take the average of all of them, if I remember my math is correct, it's 7.5 for all of them. So the average waiting time is 7.5 time units for our 3 processes. So cool. So let's compare that to what happens if they arrive in a different order. So again, all their arrival times are at t equals 0, but now to break the micro tie, I'll just assume P3 arrives first, then P2, then P4, then P1. So if I do the exact same thing again and schedule them in that order, at T0, I would schedule P3, takes 1 time unit. Then at T1, I have to pick the next process, which would be, according to my order, P2. So I pick it, it executes for its 4 time units, it's done at T equals 5. Then I pick P4, executes for 4 time units, it's done at T equals 9. And then I finally finish up with P1, which takes 7 time units, so I'm done at T equals 16. So now when I look at the average waiting time, so the average waiting time is the waiting time of all the processes divided by the number of processes. So the waiting time for P1, it waited for 9 time units, right? So it started at T equals 0 and didn't start executing till T equals 9. And then P2, it waited around for only 1 time unit. And then P3 waited around for 0 time units because it executed immediately. And then P4 waited around for 5 time units before it started executing. So the average waiting time now, if you add 9 plus 5 plus 1 plus 0 divided by 4, that's 3.75. So we reduced our waiting time by half just by changing the order, just by changing the arrival order at the same time. So it seems like the arrival order has a pretty significant impact on the average waiting time. So if you want to minimize the average waiting time, instead of just doing first come, first serve, if you want to minimize it, you do this, which is just shortest job first. So instead of first come, first serve, you'll always schedule the job with the shortest burst time first, or the shortest total running time. And again, we're still assuming no preemption. So here, I'm going to make it slightly harder, where I have different arrival times. So here I have P1 arrives at 0, P2 arrives at time 2, P3 arrives at time 4, and P4 arrives at time 5. So what I will do is just at the top of the little bars, I'll just write on their arrival times here. So this shows that P1 arrives at T0 and all the other arrival times for the processes, just to make it easier to keep track of. So now if I do shortest job first, well, I have to make a scheduling decision at T equals 0. At T equals 0, my only choice is P1 because that's the only process that's been executed. So at time equals 0, I would schedule P1 and it takes 7 time units. And while that's executing, P2 arrives, and then P3 arrives, and then P4 arrives. Now, if I take all of these processes, right, so P2 arrives before P3, but if I do shortest job first, I would prioritize P3. So whenever P1 is done executing here, I would prioritize P3 to run next because it has the shortest burst time. It only takes 1 second to execute, or 1 time unit, sorry. And then between P2 and P4, they both have the same burst time. So I'll just take them in first come, first serve order because at that point it doesn't really matter. And then, so at T equals 7, when I have to make my scheduling decision, I pick the shortest job first, which in this case would be P3. So I would execute that I would execute that for 1 time unit, and it would be done at T equals 8. So at T equals 8, now I have 2 processes left to schedule, P2 and P4. P2 became first, so I would schedule that. It's done at T equals 12. And then I have P4, which would be the last process I execute, and it's done at T equals 16. So now if I go through the average waiting time, so that waiting time for process 1 was 0, so it got scheduled at, it arrived at T0 and then started executing at T0, so it waited around for 0 time units, so its waiting time is 0. Then, and then for a little bit trickier, we have to find the waiting time for process 2. So it arrived at time equals 2, not 0 now, and then it started executing at t equals 8, so it waited around for 6 time units. And then similarly, process 3 arrived at t equals 4, started executing at t equals 7, so it waited around for 3 time units. And then P4 arrived at t equals 5 and didn't start executing to t equals 12, so it waited around for 7 time units. So our average waiting time in this case is 4. All right, everyone all good with this? So much easier than threads and locks and all that, right? So we're back to, yeah.
I just want to confirm that the burst time is the time that from the process beginning to its terminated.
Yeah, so the burst time is the total number of time units it needs to execute, which realistically we won't know, but we can evaluate our scheduling, by analyzing it after the fact. Yeah, so that's kind of what I said. Shortest job first is not practical, so it is provably optimal at minimizing the average wait time if you have no preemptions. But of course, if in real life with scheduling, you will not know the burst times of each process. So whenever the kernel executes your program, it has no idea how long it's going to take to run. So it can't schedule based off that if it has no idea. You might be able to predict past executions or predict future executions on past ones or use AI or something like that. But again, it's not going to be perfect because programs do vary wildly. And also there may be a problem where it's called starvation, where you starve long jobs. So if you do shortest job first and you have just a process that takes, 10,000 time units, and you have a constant stream of processes that only take 1 or 2 or 10 time units, well, if the small processes come in fast enough, then you may never actually execute the longest running process because it would be at the back of the queue essentially forever, which isn't terribly fair. Yeah?
So how would you know how much time a process takes before, I don't know, how do you tell the scheduler, hey, I'm going to take this long? It's something like kernel level.
Yeah, so realistically you won't know, which is what makes scheduling even harder. So this is, for now we get to live in the nice world where we'll know and we can use it to evaluate. So typically people do a workload and then keep track of how long it takes and then simulate it a bunch of times. So that's how you would actually evaluate it. But they're we'll get into more of it, but there's no perfect answer for a scheduler. Yeah?
That's probably, right? Or is that a real word?
Provably.
Provably. Nice. Sorry.
That's okay. It is provably optimal. All right, so we can tweak it so that it runs. So we've been talking about non-preemptible processes. Of course, we know our processes are preemptible. So we can tweak it, shortest job first to deal with preemptible, and we'll do something like shortest remaining time first. So you assume that, again, we'll just assume the minimal execution in time is 1 time unit. So in this case, for preemptible processes, shortest remaining time first is provably optimal to minimize the average waiting time. So let's see what that tweak is. So the tweak with shortest remaining time first, it means when a process comes in, you're allowed to switch the current running process and essentially context switch it out. So here, and throughout the whole lecture, we'll use the same arrival times and burst times for the whole thing and see how our scheduling changes. So now if we do shortest remaining time first, well, let's start at t equals 0. So at t equals 0, again, we just start executing process 1. We have no other choice. That's the only process we can run. So we would run it for 2 time units until process 2 comes on. So at t equals 2, when process 2 wants to start, well, we would pick the shortest remaining time first. So P1 still has 5 time units left to execute because it takes 7 and it already executed for 2. So it has 5 left. And then process 2 has 4 time units remaining. So we would context switch out P1 and start executing P2. So P2 would execute for 2 time units until process 3 comes in. So process 2 now has 2 time units remaining, and process 3 only takes 1 time unit to execute. So the process with the shortest remaining time is now P3. So we would just execute P3 immediately and then switch back. And also P4 would come in at the same time, which now has 4 time units remaining. So we would pick the shortest remaining time first. So P2 only has 2 time units left, so we would just finish it up quickly. And then at t equals 7, we would have the next shortest remaining time first, which is P4. That takes 4 time units, so we'd run that. And then at t equals 11, we would just finish up P1. So now our average waiting time, we have to do a bit more math, so we can either, so the the wait time for process 1 is essentially this whole middle section. So it started here, and before it finished here at t equals 16, it had to wait 1, 2, 3, 4, 5, 6, 7, 8, 9. So it had to wait 9 time units, or if you don't want to count the squares, so it finished at t equals 16 and wanted to start at t equals 0. So you just take that difference and subtract how long it takes to execute. So 16 minus 7 is 9. So it waited around for 9 time units. P2 only waited around for 1 time unit because we started executing it immediately, and then it waited around for 1 time unit while P3 was executing, and then it finished up. And then P3 waited for 0 time units. As soon as it came in, we scheduled it immediately because it was very, very quick. And then process 4 waited for 2 time units. So it came in at t equals 5 and started executing at t equals 7. So our average waiting time in this case is 3. So any questions about that? Little bit trickier because there's little gaps, right? Okay, so this is as hard as we'll get today. Round robin, which is kind of what you did in lab 2. Yeah.
Why P4 wait for 2 CPU cycles plus P3 didn't?
So the question was, why does P2 wait for
P4.
P4 wait for 2 CPU?
Because P4 can at arrow time is 5, but it runs at 7.
Yeah, so it waited for 2, right?
But why P3 is just immediately run at when it's arrived?
So P3 came in at t equals 4.
Yeah.
And at this time, we had P1 and P2 that had some time left. So P1 came in here and had 7 time units and then executed for 2. So it still has 5 time units left it needs to execute. Then P2 came in, it had 4 time units it needs to execute, which is shorter than 5. So we scheduled it. So it ran for 2 time units. So now it has 2 time units left, and then when P3 came in, it only needs 1 time unit to run, which is shorter than all of them, so it just schedules it immediately. So as soon as it prioritized the shortest job, or the shortest remaining time. So the short task, we just switch to it, we get it done out of the way, and reduce our average waiting time. So like before here, our average waiting time, since we can preempt stuff, was 3. In this case, it was 4. All right, so far, the scheduling has been 1, not super realistic because we won't know how long stuff takes. And then 2, it isn't super fair. It has that starvation issue where long-running processes may never execute. So if you want to handle fairness, one thing you can do is just round robin. So you essentially divide the execution up into time slices, which are called quanta. Don't ask me why. Computer scientists want to use fancier words than just time slice. Who knows? They're weird people. So an individual time slice is called a quantum. Again, I don't know why they want to make things difficult. But all you do is maintain a FIFO queue similar to first come, first serve. And you just circle back in the queue again and again and again and just serve them in order. But instead of running everything into completion, you just give everything a time slice and try to be fair by just divvying it up between all the different processes. So given your time slice, you just give a process of a time slice, let it execute for that time slice. If it finishes, great. If it doesn't finish, you just re-add it to the end of the queue when it's done. And this is the first scheduling algorithm that's actually used in the Linux kernel. So this is like the simplest scheduler you can use, and it is a perfectly valid one. If you had to implement your own schedule for your own, I guess, threading library, you pretty much already did this, right? So this is where that comes from. So what are some practical considerations for determining the quantum length, or like the length of the time slice? Yeah.
I guess there's a penalty for every time you context switch, so it should be shorter than penalty.
Yeah, so there's some penalty for context switching, which is some overhead, but the quicker or the shorter the time length, the better my response time is going to be, right? And then what happens if my quantum length is essentially infinite? Well, then it becomes, yeah, then it essentially becomes exactly first come, first serve, right? Which is pretty terrible. So there's, and yeah, so if you have the quantum length really, really low, you'll have a lot of context switches, you'll have good response time, but you'll have a lot of context switches. And if it's too large, then you're essentially going to have first come, first serve, which is kind of a crappy scheduling algorithm. So let's go through this and do round robin with a quantum length of 3 time units. So again, I have the arrival times at the top, and I'll just write it out just to make it easier. So let's do round robin with the quantum length equal to 3. So my time slice, whenever I schedule a process to run, it will run for at most 3 time units before I take away and context switch it out. So at t equals 0, so right here, whoops. So right here at t equals 0, my queue is just going to be P1 because it arrives at that time. So if I need to pick a process to run, I have no other choice but to pick P1. So I would pick P1 to run for 3 time units. So at the bottom, at each one of these, I'll write out the queue at the bottom. So at t equals 2, my queue would have been empty, and P2 came in, so it just goes to the front of the queue. Then at T3, whenever P1's time unit is done, it would get re-added to the back of the queue. So now my queue would look like P2, then P1. So when I pick the next, OBS crashed. All right, so we are back. No, they're still recording. I resumed it. It's saved. Okay, so at t equals 3 here, in our queue, there's P2, P1. So we would pick P2 to execute for its 3 time units because it takes 4 time units to execute. And then while that's going on, right after we schedule it, we would take it off the queue. So P1 is next in our queue, and then at t equals 4, P3 comes in, so it would go to the back of the queue. So our queue would be P1, then P3. Then t equals 5, P4 comes in, so it would be added to the back of the queue. So at t equals 5, that's what our queue looks like. And then at t equals 6, whenever process 2 is done its time slice, it would be added to the back of the queue. So our queue would look like this. So it would be P1, P3, P4, P2. So we pick off whatever is at the front of the queue. So it's P1, which executes for another 3 time units, which brings us to t equals 9. So our queue at that point would be P3, P4, P2, and P1's still not done executing, so it would just add itself to the back of the queue. So P1's at the back of the queue. Now P3 is the next one to run, it only lasts for 1 time unit. So it would just be scheduled, run for its 1 time unit and be done. Now our queue just has P4, P2, P1. So we would execute P4 because it's at the front. So it would execute for its 3 time units. Now we have P2, P1, P4 in our queue. So we would execute P2, which just has 1 time unit left. It's done. So now we just have P1, P4 in our queue. We execute P1, and P4 is the only thing left in our queue. We execute that, and then all our processes are done. So any questions about that? Yeah.
How do we determine what quantum?
You're told that. So it's like, what's the scheduling if the quantum length is 3?
Would this be like a fair quiz question?
Yep. This is,
So what's the optimal quantum?
depends on the processes. So if we want to make you waste time, we could say, hey, try do this for all the quantum lengths and tell me what the best ones are for this process. That would kind of be mean, though. Hopefully that doesn't actually happen. But usually, weirder things have happened. But so if we want to calculate, waiting time, so usually there's 3 metrics you want to calculate when you do this. So it's average waiting time. So our average waiting time here would be for P1. So how long did P1 wait? Well, if we count, so it started here. So P1 started executing there and didn't finish until here at t equals 15, right? So P1, it waited around for, was that 15 minus 7, so it waited around for 8 time units, right? Yeah, so P1 waited around for 8 time units. P2, how long did it wait around? Well, it started here at time 2. It didn't finish until P equals 14. So 14 minus 2 is 12, and it took 4 time units, so it also waited around for 8. We could also just count the number of time units it waited around for when it started. So if we count, so it started, we wanted it to execute at t equals 2, so it waited here at that yellow mark. So 1, 2, 3, 4, 5, 6, 7, 8. So it waited 8 time units until it actually executed, right? So P3, how long did it wait? Well, it waited around for hopefully 5. So it started at t equals 4. So it waited here, 1, 2, 3, 4, 5. So P3 waited for 5 time units. And then finally for P4, how many time units did it wait? Well, it waited for 1, 2, 3, 4, 5, 6, 7. So it waited for 7 time units. So if we do that for our average waiting time divided by 4 would be like 7. So next thing we would do is average response time. So for P1, so response time is just whenever it arrives and then how long it took to start executing. So this is less we have to count. So for P1, it waited around for 0 seconds until it first started executing. So it's a 0. P2, how long did it wait for? Well, it arrived at t equals 2 and started executing at t equals 3. So it only waited around for 1 time unit. P3, well, its waiting time is the same as its response time, so it waited around for 5 time units again. So it arrived at t equals 4 and didn't start executing at t equals 9. And then finally for P4, it arrived at t equals 5 and didn't start executing until t equals 10, so it also waited around for 5 time units. So if we add all those together, it's 11 divided by 4, which equals like 2.75. And then the other metric we might want to keep track of is the number of context switches. So that's only when we change between processes. So if we count the number of context switches, there's going to be 1 here between process 1 and 2. So 1, 2, 3, 4, 5, 6, 7. So there are 7 context switches. All good? Everything makes sense? Cool. So let's do it again, as hard as it's going to get. So here's your question. What happens when you change the quantum length? So given all of our metrics, let's do it with the quantum length equal to 1. So this is just going to be the exact same process, but just a lot more writing. So let's do it again because that was so fun. So t equals 0. There's only one process. It would just go to the front of the queue. So it would execute. Then at t equals 1, it just gets shoved to the back of the queue. So there's only one process again. So it would execute again for its 1 time unit. Now, at t equals 2, process 2 comes in. So it would go to the front of the queue. And this is like kind of a tie where a new process is coming in as you're re-queuing yourself. So in this case, you would prioritize the newer process just to get its response time down. So in this case, at t equals 2, P2 arrives, and then P1 re-adds itself to the back of the queue. So our queue would look like this. It would be P2 followed by P1. So we would schedule in process 2. Then our P1 would be in our queue, and we would re-add P2 to the back of the queue after it's done its 1 time unit. So then process 1 would execute for its 1 time unit. And then here, our queue would have process 2 at the front, and then process 3 comes in. So we would add it next, and then re-queue process 1 at the end. So is everyone on the same page for that one? So this is as hard as it's going to get today, so we can breathe a sigh of relief. So that's our tie. We pick the process that is at the front. So process 2 would execute. Now our queue has process 3, process 1. Now we're also re-adding process 2 to the back of the queue while process 4 arrives. So we'll prioritize the new process. And then our queue looks like this. So everyone good with that? Now, P3 is going to execute for its 1 time unit. It only takes 1 time unit it's like total running time is only 1 time unit, so it's done now. So thank Jeebus, we don't have to worry about that in our queue. So now our queue is 1 shorter. So now we just, essentially this is where the round robin is. We're just going to go around and around and around until everything's done in the same order. So P1 executes, and we have P4, P2, P1 in our queue. So P4 executes. We have P2, P1, P4. So it's going to go 2. Right, and at this point, we always know it's going to go 1, 4, 2, 1, 4, 2, 1, 4, 2 until they're done. So 1, 4, 2, 1, 2, 3, 4. So at this point, after this 1, 4, 2, process 2 is now done. So our queue would just look like process 1, then process 4, because process 2 is executed total. It's 4 time units, so it's done now. So now we just are round robbing between process 1 and process 4. So it would be 1, 4, and at this point, 4 still has 1 time unit remaining. It's not done yet. And then 1, 4, and now they're both done. All right. So everyone agree with that? All right, so now we can do our average waiting time. So what's our waiting time for P1? Yeah. Yeah. Average waiting time for P1 is 8. So it finished here at t equals 15, started at t equals 0, and it took 7 time units. So, and of course, if you just count the number of time it is just waiting around, it's 1, 2, 3, 4, 5, 6, 7. Whoops, I highlighted 1. 1, 2, 3, 4, 5, 6, 7, 7, 8. All right. How long did process 2 wait? I think I heard a 6. How long did process 3 wait? 1. That was easy. All right, process 4. I heard 7. So if I do that, divide by 4, 5.5. Cool. So next, average response time. So what's our average response time now? So how long did P1 wait till it started executing? Big ol' 0. Process 2, also 0. It arrived at t equals 2. It started executing immediately, so that's cool. What about process 3? 1. So it arrived at t equals 4, executed at t equals 5. So it waited around for 1. What about process 4? 2. So by doing that and calculating that, it appears that our response time, we lowered the quanta, and our response time got way better from before, right? So now our average response time is 0.75, while before it was 2.75. So our response time is way better now. Our average waiting time went from 7 to 5.5, so that also improved, but it doesn't necessarily improve. And then finally, we need to count the number of context switches, which, if we were correct before in our argument, there should be a lot more context switches, and there should be because I had to write a lot more. So that's one context switch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Whew. So, whoops. So, our response time and average waiting time both went down, but our number of context switches went way up. So this is, when we do this, we assume our context switches are free, which we know they aren't. Yeah.
So is P1 running for two units only because, for the first two, only because there's no other processes at that point, right?
Yep. Yep. So P2 runs for 2 time units in a row there just because there's no other choice. So, yeah.
Why is the average response time a useful metric? I thought what we mainly care about is when the process ends, not when it begins.
So you would care about when it begins if it's like an interactive application. So like if I click a mouse, when do I see some response? So you don't really care when Firefox ends, you care when you see your mouse movement or something like that. And it's probably more realistic than average waiting time, unless it's like you're just doing pure computation. So this crux of like doing pure computation versus user interaction is kind of what we'll see in more advanced scheduling. All right, so let's do it again. So quantum length of 10. Well, this case should be a lot simpler. So if we did have quantum length of 10, it's essentially first come, first serve. So it's essentially first come, first served without preemptions because they'll just execute until it's done. So this will look exactly like the first example of the day where we have P1 that comes in because it's the only choice at t equals 0. Then after that, it's just the processes in order because it's first come, first serve. So P2 would execute, and then P3 would execute, and then P4 would execute. So if we do that, compute all these metrics again, there's only 3 context switches now, which is a slight improvement, but our average waiting time actually went down slightly, but our response time shot way up. So it was like 2.75 for quantum length of 3, and then 0.75 when the quantum length was 1, and now it's 4.75. So this was the same case as first come, first serve without preemptions. So the round robin performance depends on the quantum length and the job length. So people have simulated this before, so even with round robin, it's a bit difficult to argue about in general. There's no perfect answer. So round robin has like a fairly good low response and good interactivity. It has fair allocation of the CPU and a low-ish average waiting time when the job lengths vary, which is just found through simulation. But the performance does depend on the quantum length. So too high, it becomes first come, first serve. And then too low, there's way too many context switches, which is just a lot of overhead. So you probably typically on a real system, you want the overhead to be like in the single digit or less percentage. And then just a fun thing you find from simulations is round robin has a really poor average waiting time when the jobs have similar length. And that's, again, just found through simulation. So scheduling does involve a bunch of trade-offs. Today is like the basic scheduling. We'll get into fun stuff next lecture. I guess it's tomorrow. But we looked at a few. So there's first come, first serve, most basic, stand in line at the food truck. Shortest job first, so that's a tweak to provably reduce the average waiting time. And then if you allow processes to be preempted, you could tweak it so that you have shortest remaining time first. And that will, again, optimize the lowest or waiting time. And you also might see it called a turnaround time, so total time from when it starts to when it finishes. And then we saw round robin, which tries to optimize fairness and response time. So that's it. And just remember, I'm pulling for you.